Okay, we are now looking at organic chemistry. We did the inorganic chemistry. This is a very long PowerPoint, over 200 slides, 240 some slides. So we won't do all of these, but I'll just kind of skim over. Primarily, I want you to really read your textbook, but the slides will elucidate some points that are of importance. This first part we've already seen in my last one, the fields of chemistry separated between inorganic and organic. Organic chemistry, all the compounds contain carbon in an organified way, which means they're really hydrocarbons, as you see here. Okay. Under organic chemistry, we have biochemistry, polymer, geological, all containing carbon, all coming from living entities at one time. Our interest is in chemistry today, the living right now, which falls under biochemistry. However, biochemistry can be for plants and animals. Our interest is human biochemistry, so that's what we're set at here. Under the human biochemistry, there are many aspects. The textbook is actually, in a full biochemistry course, is as large as your A&P textbook. So primarily the only things we'll be discussing are these, what we call macronutrients known as carbohydrates, lipids, nucleic acids, and proteins. So that's all we will discuss under our biochemistry, organic chemistry. Now, there are certain commonalities among these. One is a monomer to polymer relationship, and the other is the interaction of water into chemical reactions. I may have some videos to show you besides this one from other sites that can kind of help you. Organic chemistry, we talked about different kinds of bonds before, ionic, covalent, hydrogen. Organic chemistry is a covalently bonded chemistry. Everything in it has a covalent bond. Okay? So the monomer to polymer, interaction of water. Okay, the monomer to polymer relationship. A monomer is an individual unit capable of repeat. Now the monomer itself is a molecule, not just an atom. It's actually a molecule. And so these molecules are hooked up by, quote, covalent bonds to make a polymer. Polymer means many. So when you look at that, here would be a monomer example, and here I'm trying to schematically show you a polymer, and this would be a chemical bond, which would be a covalent bond. When we get to carbohydrates, the monomer in a carbohydrate would be a molecule like a monosaccharide. Glucose is an example of one molecule. Then the polymer would be something else. The polymer could be glycogen, which we store carb with. Okay, so study on that. The interaction of water. Water is very important. We named it in the last section. But one thing water can do is insert into these polymers. And when a water molecule inserts, it splits apart, sometimes called hydrolysis, and can separate the polymer into individual monomers. So some people will call it a hydration decomposition, because you're adding water, hydrating, and it's breaking apart, or hydrolysis, you're splitting the water when it enters decomposition. So water participates. When you pull the water out, let's go here. So when you pull the water out, let's say, it could go the opposite way. So here's another example. Hydrolysis, so that water is coming in and breaking the thing apart. Hydrolysis, breaking the polymer. Removal of water would then put things back together. Of course, you call it dehydration synthesis, some will call it. An anabolic building reaction. So you can see that again here. Removing the water puts it back together. Dehydration reaction. So glance at that. Here's again some more demos of that you can do on your own. I don't have to really work with you on that. Okay, next we go to chemical formulas. Okay, we have several types of chemical formulas. One is called the empirical formula. In the empirical formula, you mainly name the atoms by symbols. Those symbols came from the periodic chart, but only give a relative number of atoms. Okay, just the relative. The molecular formula is where you name the atoms by symbols and you give the exact number. Then both of these can be done on a two-dimensional surface. The structural formula is done on a two-dimensional surface, and it is an attempt to try to explain a 3D structure with a 2D flat structure, a drawing. And if you want to do better than that, you actually go to models. Okay, so let's talk about that. Okay, let's use glucose as our example. Let's use sugar as our example, glucose. The glucose formula is C6H12O6. That is the actual formula of glucose. Okay. The empirical formula, relative number, would simply be CH2O, because there are twice as many hydrogens as there are oxygen and carbon. The molecular formula, which gives the exact number, would be this formula right here, the C6H12O6. The structural formula would be on a two-dimensional surface, attempting to display that on a two-dimensional surface. Okay, and then a model would come in and show something on a three-dimensional surface. So again, here we're looking at something like methane. Here's a structural formula, and here you're looking at the model type of deal. Here's the molecular for methane. Here's the molecular for the exact number, structural, trying to show on a two-dimensional surface. So I just wanted to kind of point that out to you in that particular aspect. Now, carbon forms the basis of our molecules. It forms the basis of the molecules in organic chemistry. Why? Because carbon has four electrons in its outer shell, so it needs 4 more. So it has a lot of bonding diversity. Shall I say this? You could bond at 4 different sites, different things. And you actually could bond 2 things at the same site. So it is believed the reason that carbon was picked as the structure more of life chemistry, I guess you could say, is because of that. Now, in many cases, carbon binds to carbon to form something in organic chemistry called a carbon backbone. You know, whoever looked at it said it kind of looked like our vertebrae and our backbone. So a lot of that, but you still need some more bonds. Because see, in this case, this only has 1, so I need 1, 2, 3. So carbon has a tremendous amount of diversity that it can do. So that gives you an idea of that. Okay, next we go to functional groups. Functional groups are, to say it in this way, it's a group of atoms bonded together, hooked to a carbon backbone, and their chemical behavior is the same no matter what carbon backbone you hook it to. So it would be something that behaves in a certain pattern, like these here, and you can hook them to a carbon backbone, and no matter if the backbone looked like this or it had a different structure, the way the functional group would behave would be the same in all circumstances. So that's what we call a functional group. I'm going to discuss a functional group in the next video. Thank you very much.